What are you actually talking to when you type into a terminal window? See, for a lot of developers, the terminal can feel like a bit of a magical black box. You recite a series of incantations and it just does stuff. It even seems to know who I am. Okay, fair enough, but it's not magic, it's a program. And once you understand which program and what it's actually doing, a lot of stuff that may have felt like magic before can start to feel obvious. The word terminal is actually somewhat of a historical accident. It refers to the physical hardware terminals that people used to connect to mainframe computers. Obviously, we don't have those anymore, but the name terminal stuck around. Modern terminals are just applications that emulate the behavior of those ancient devices. A terminal emulator handles the visuals, such as fonts, colors, and scrolling, but it doesn't actually interpret any of your commands. That job belongs to a separate program running inside the terminal, called a shell. The name shell comes from this program's role as sort of a protective outermost layer of the operating system. It sits on top of the kernel, which is the core that actually manages your hardware, your running processes, and your files. The shell accepts your text as input and translates it into clean requests that the kernel can understand. And in this way, the kernel never has to accept raw human text as input, only the shell does. Before we go any further, it's probably worth defining exactly what I mean when I say file, program, and process, just to prevent any potential confusion. A file is organized data stored on disk. It could be some text, it could be an image, some source code, anything really. A lot of people think that there's something special about different file types. Perhaps they think that a JPEG file is fundamentally different from a PNG, for example. But really, all files are just bytes. The difference between any two file formats is just how those bytes are arranged. And it's always up to the application consuming the file to decide how to interpret it. A program is a file too, just one whose bytes happen to be instructions that the computer can execute. For our purposes, the term program and the term executable file are synonymous, although sometimes you'll hear program referring to a source code file that hasn't been compiled yet. Finally, a process is what you get when a program actually runs. The program file on disk doesn't do anything by itself other than just sit there. A process is that program file loaded into memory and actively executing, with its own memory allocation and its own status in the operating system's sort of list of running things. As we said, the shell is a program, meaning that somewhere on disk there's an executable file containing every instruction that defines how the shell behaves. We'll discover exactly where this file is in just a second. And like any other program, the shell runs as a process. When people refer to the shell, they're typically referring to this process. The shell process has its own ID, its own memory, and the ability to spawn child processes, which is a detail that'll matter more once we start actually running commands. Shells come in a few different flavors, which is really to say that there are multiple distinct programs that all fulfill the role of a shell. The two most common are called Bash, which is default in most Linux systems, and Z shell, which is the default in Mac OS. The differences between any two big shells at this level are mostly invisible, meaning the concepts here should apply across all of them. You can find out which shell your system runs with a single command, echo $shell. For me, this returns /bin/zsh, which is the location on disk where the actual shell program lives. We'll explore file paths properly in the future, but for now, just know that this type of string represents a unique location on disk. In this case, it's the location where the shell program file actually lives. There are really three things to unpack here. There's the command echo, the $sign, and the word shell. So let's start with echo. Echo is a command that simply prints its arguments back to the screen. For example, we can echo out a few words like so. Echo 123 will simply print 123 to the screen. We can also echo strings like this. Echo is a useful command, and it's also a very simple command. There's really not much more to it. So that raises the question, if echo $shell printed /bin/zsh, then how did $shell become /bin/zsh? To understand that, we need to talk about environment variables. An environment variable is a text variable that the shell stores in its process memory. And do take note that it is a text variable rather than a number, an array, or anything else. This fact will arise again and again while working with the shell. Internally, the shell maintains a map from variable names to values called the environment, and the name shell is one of the entries in this map. We can use a command called printenv to examine the map. Printenv stands for print environment, and will print the entire map in a key value format like so. Definitely don't worry about memorizing every entry here. There can be an awful lot of environment variables. And in practice, most of them are set by the operating system or your shell configuration anyway, so the exact contents tend to differ significantly across systems. Here, just take note of the shell entry in this map. We can also run printenv directly with a variable's name to see its value. As expected, this returns the same /bin/z shell as before, although last time we used the $sign to get there. The $sign is called the expansion operator, and it simply instructs the shell to replace a variable's name with its value. Hence, $shell was substituted into /bin/zsh via the internal map before echo was ever called. We can also create our own variables pretty easily. The syntax is just name equals value. And once again, we can use the expansion operator to access the value that we assigned. Notice that there aren't any spaces surrounding the equal sign. That's because the shell uses whitespace to separate commands and arguments, so this, for example, would be invalid. We can also use printenv to examine our new variable. Except, this doesn't seem to return anything, so why not? What's the difference between shell and name that causes printenv shell to print the value associated with the shell variable, but printenv name seems to print nothing? Well, it turns out that I lied to you earlier when I said that printenv will print the entire environment. It actually only prints a subset of the whole environment map. But it's not really printenv's fault, and here's what I mean. As the shell maintains its internal map of variables, it also marks each entry as either exported or not exported. The difference is that exported variables are exported to child processes. When you type the name of a program, the shell process spawns a new process to run that program. And that new process is called a child process, because it was born from the parent process. Exported variables are the ones that get passed from the shell down to child processes. That's why printenv name produced no output, because the process that ran the program called printenv never knew what name was, or that it even existed for that matter. We'd get the same thing if we ran printenv with some nonsense variable name, like this. It's common to refer to an exported variable as an environment variable, and to a non-exported variable as a shell variable. We can promote a shell variable into an environment variable using the export keyword. For example, export name. Now, of course, because name was exported, it will be passed along to printenv's process. All of this raises a worthwhile question, which is, why would one ever want a shell variable not to be exported? Before we answer that, though, let's take a breath and pull together everything we've built up so far, because it's not lost on me that this material can pile up fast. We started with the terminal application and found that the real work happens inside it, in a program called the shell. The shell is a program, which means that it's a file on disk full of instructions, and when it runs, it becomes a process, with its own memory and its own identity on the operating system. The shell's fundamental job is to be a text-based interface to that operating system, which is a big part of what makes it so powerful. It works by reading the text that you type and parsing it into commands, arguments, and variables. Those variables are stored in the shell process's memory in a map that we call the environment. That map is what lets us make sense of our very first command, echo $shell. We found that echo itself doesn't do anything clever, it just prints out the arguments it was handed. The real work happened one step before, when the shell saw the $sign and treated the word shell as a variable, looked up its value in the map, and only then returned the result to echo. We also saw that we can define our own variables, since the shell isn't just an interface, but it's also a scripting language in its own right. And that's where we hit something interesting. Our new variable worked with echo, but it showed up empty with printenv. The reason comes down to the fact that printenv doesn't run inside the shell at all, but but instead runs in a child process of the shell. And child processes only receive the variables that the shell explicitly gives to them. Since we never exported name, it stayed local to the shell, and printenv had no way to see it. Which brings us right back to the question that we paused on. Why would we ever want a shell variable not to be exported in the first place? The answer comes down to how you conceptualize what exactly the environment is. We know that it's a map, and we know that it stores text variables, and we know that it belongs to the shell process. But it's not some type of shared global state. It truly belongs only to that shell process where it was created. When the shell spawns a child process, it passes a snapshot of its exported variables to that child. Changes in the child won't propagate up, and changes in the parent after spawning the child won't propagate down. If you think about it, this means that some variables simply shouldn't be exported. Take, for example, this variable called ppid. Ppid stores the process ID of the current process's parent. You could imagine then, if a child process inherited ppid from the shell, it would be carrying around the shell's parent's ID as its own parent's ID, which, from the child's perspective, is simply incorrect. It's for this reason that I tend to think the term environment variable is a bit of a misnomer. Fundamentally, the shell's environment isn't something that a child process lives inside so much as a snapshot that it's handed at birth. If the shell were to spawn two children, two siblings if you will, each one would get its own independent copy, and neither sibling could see the other's variables. And once they're running, neither can see the changes that happen back in the shell. Every process just carries its own private snapshot forward. At this point, the astute viewer might just be swirling with questions. Does the shell itself have a parent process? And if so, where does the shell get its environment from? What happens when a child process spawns a child of its own? Does the environment just keep passing down the chain? Do child processes themselves have a notion of exporting? These are all great questions, and they get at something deeper. This whole parent and child process story doesn't start at the shell, and it doesn't necessarily end at printenv. We'll get to all of that in the future. For now, I really want to solidify this idea of the environment as a snapshot and of environment variables as nothing more than just text. The best way to do that is to get our hands on the environment directly by writing our own program that reaches into it and prints it out. Our own version of printenv, if you will. The main function is the entry point for a C program. And as you may already know, it can take two arguments, usually called argc and argv. Fewer people know, though, that on most systems, main can take a third argument called envp, or environment pointer, and this one holds the shell's environment. It arrives as an array of null-terminated strings, each one a single key equals value entry, which means that we can just iterate through the array and print them out one by one. And just to give the program our own little touch, let's print each entry in gold. Once we compile and run it, you can see that it produces essentially the same output as the real printenv program, just in a different color. It's worth mentioning that this is only one way to reach the environment from a C program, and it's not even the most standard one. But it's probably the most illustrative. And after all, much to my chagrin, this is not a C programming video. This new program leaves us with a problem. We have a newly minted printenv program, which prints the environment in gold, and the system has a program called printenv, which prints in white. So when I simply type printenv, which one runs? As we can see, the system's printenv won. So let's figure out why. There's a command called which that takes the name of another command and returns the exact location where the shell finds the corresponding program file. Running which printenv shows us exactly which program called printenv the shell reaches for. And it works on other programs too, so we could just as easily locate zshell, for example. Or if you're feeling a little recursive, then we can locate which itself. But this only tells us where the shell found each program, not how it knew where to look. So how does the shell take the bare name of a program like printenv and turn it into a path into an actual location on disk. Before I show you, I want you to think about how you'd solve this problem if you were the one designing the shell. One approach that you could try is to map every command name to a path using something like a shell variable. For example, if we set printenv to this path, then we can simply call it by referencing that shell variable. But this isn't great. The very fact that I was allowed to do this, first of all, means that it's not what the shell actually implements. Beyond that, though, under this model, every command would now need a $sign in front of it, and the shell would be holding a separate variable for every single program that we wanted to recognize. Another idea would be to have the shell search the entire machine from top to bottom every time you run a command, looking for a program with a matching name. But, of course, that's punishingly slow, and it doesn't say what should happen when two programs both go by the same name, let alone what should happen if there's a file with that same name that isn't even executable. We could fix both of those problems by picking one single directory and declaring that all programs must live there. And while this is closer to the real solution, it's rigid in certain ways that will cause real operating system level trouble. The sort of trouble that we'll get into more later when we explore the file system properly. So that's not quite the answer either. What the shell actually does is sort of a blend of these approaches. It keeps a short list of directories to search through, called the path, and it exposes that list as an environment variable, so you're able to modify it. Whenever the shell needs to locate a program, it walks the directories on path, one by one in order, and it stops at the first match. So let's take a look at this path. Notice that it's a single colon-separated string rather than an array or list, once again because all environment variables are only just text. Looking at it closer, we can see that /user/bin is on the path, but our current directory isn't. And that's why the system's printenv beat ours just a moment ago. But say we really do want the environment printed in gold. Since the shell reads path left to right, we can hijack the system's printenv by putting our current directory at the very front of path. We can do that like so. Let's read this line piece by piece. The dot is shorthand for the current directory. The colon separates it from everything after, and of course $path expands to path's current value. So what we're really saying is take the current directory, then everything that was already on path, and reassign all of that back to path in that order. This is a pattern that you'll see constantly while dealing with package management and shell configuration. The current directory now sits first, so the shell checks it before anywhere else. And sure enough, which printenv now points at our current directory, and running printenv gives us our gold output. This, as it turns out, is exactly why your current directory isn't on the path by default to begin with. Omitting it is a deliberate security decision. If the current directory were on path by default, then any stray program sitting in whatever random folder you happen to be in that shares a name with a program that you trust could run in its place without you ever realizing it. And finally, in the name of science, let's see what happens if we wipe the path variable out entirely. So, what would happen now if we were to run which_zsh, for example? Surely, we'll just get a tidy little error telling us that the ZSH program can't be found, right? Well, we would, if the shell were able to find which in the first place. Which itself couldn't be found by the shell, let alone called upon to search for anything else. It's worth noting here that on some systems, which is actually built into the shell, rather than implemented as a separate program. On these systems, you'll find that which actually still works here, since the shell doesn't have to search for it at all. In any case, we can always call a program directly by its path like so. Now, which runs correctly, but since path was empty, it was unable to search for ZSH. The whole point of this exercise is to demonstrate that path is not just how which finds your programs. It's also how the shell finds which, and by extension, how the shell finds your programs too. So if you're ever running into any command not found errors, or you expect one program to run, but actually another program runs, the path is usually a good first place to check. This has been a lot of material for one video, and I hope you found it valuable. But before we wrap up, I want to leave you with just one more tool, and I think it's one that'll serve you well no matter where you decide to go from here. Nearly every command that we've run today, and nearly every command you'll ever encounter, comes with its own built-in manual. To open it, just type man followed by the command's name. I'd really encourage you to get comfortable with man pages. They're often faster than reaching for a search engine when you have questions about commands, and they're virtually guaranteed to be accurate for the exact version of the tool that you have installed. Once you're inside a man page, you can use the arrow keys to scroll up and down, and press Q to go back to your shell. And of course, if you ever forget how to use a man page, simply check out its man page. So, what are you actually talking to when you type into a terminal? You're talking to a shell, which is a program that's running on your machine, it's part of your operating system, and whose whole job is to take the text that you give it and translate it into an action, dispatching to other programs to get things done. Thank you for hanging with me all the way to the end. As always, if you've got questions or comments, please do leave them down below. And if you've enjoyed this video, a subscription genuinely helps a lot, and it means that you'll be around for what's next, because there's so much more to explore here, from the file system, the process tree, how processes talk to one another, as well as more hands-on tools like SSH and tmux. And of course, if there's something in particular you'd like to see covered, I'd love to hear about it. With that, I do hope you've enjoyed, and please take care.